In this lesson, we'll continue our discussion on big idea number 2, talking about the rate of chemical reactions and describing them quantitatively. And then we'll also touch on big idea number 2. How can you manipulate a reaction to make it go faster or slower? That takes us to learning target number 4. By the end of the lesson, you should be able to describe the factors that affect the rate of reaction and explain why each works at the molecular level. We often take for granted the fact that we can mix two reactants in a beaker and instantly see a reaction form. In order for reactants to complete a reaction and form products, the following conditions must be met. The reactant particles must collide with each other. This is known as collision theory. This is not as easy as it sounds. Remember, particles can have vibrational, rotational, and translational motion. They move randomly in three-dimensional space. They do not have consciousness. Therefore, if I react particle A and particle B together, sure, A will collide with B, but a lot of A's will hit a lot of other A's, and a lot of B's will hit a lot of other B's. So not every collision will produce a reaction. Secondly, reactants must collide in one particular way in order for the necessary bonds to form in the products. This is known as collision geometry or orientation theory. If they don't collide properly, the reactants will just bounce off of each other and no reaction will happen. Condition number 3. Reactants must collide with enough kinetic energy to break the bonds in the reactants. This is known as activation energy theory. If they don't hit at the right speed, they will just slide past each other or bounce off of each other. Now, if conditions 1 to 3 are met, reactant A and B collide at the right orientation with the right activation energy, then a highly unstable chemical species is formed with partial bonds. This is known as transition state theory. This temporary chemical is known as the activated complex, and it only has a 50% chance of falling into the products, or just back into the original reactants. So how is it that we can have reactions that we just mix two reactants together and we get a reaction? Well, we often use billions and billions of particles, because the more collisions that happen, the better the chance that a proper collision is going to occur. We can take these steps during a chemical reaction and expand on the energy diagrams that we were drawing in the beginning of the unit showing the enthalpy change. We can now include activation energy and transition state theory onto our energy graphs. Here are some examples. Because the reactants have higher energy than the products, this is an exothermic example. The difference between reactants and products is shown on the graph as being our delta H value. All we've done over our previous graphs is just move our products over to the right hand side, and we've put time on the x-axis. When reactants collide and hit each other, they slow down, and their kinetic energy is converted into potential energy, which can be used to break bonds. This is why you see this hill. At the top is known as the transition state. This is where the activated complex exists. The energy difference between the reactants and the transition state is known as the activation energy of the forward reaction. There's a little FWD there. If your reactants collide at the right orientation and the right activation energy, they will be able to climb up this hill and reach the transition state. then the activated complex that exists here has a 50% chance of sliding down either side of the hill, going back into reactants or changing into the desired products. Now, if I really wanted to, I could make an exothermic reaction run backwards and create an endothermic one. The activation energy for going in the reverse direction would be climbing up this hill to get to the transition state. That's why the energy difference between the products and the transition state is labeled as the activation energy of the reverse reaction. Now, you do have some equations in your textbook where you could sub in values and rearrange. They would give you two of these numbers of these three values, and then you could rearrange and find the missing one. But because this is a graph, it's a scale diagram, which means that these differences here you can treat as vectors. So say, for example, I have the enthalpy change and I have the activation energy of the reverse reaction, and I'm asked to find the activation energy of the forward. All I would do is subtract this number from that number. Next door is an example of an endothermic graph. I know that because the energy of the products is greater than the energy of the reactants. That means that my system has gained energy. Let's have a look at example number 1. Chemists are able to control the rate of a reaction by changing the probability that successful collisions occur. This can be done by changing any of the following factors. The first being reactant concentration. If you increase the concentration of one or more of the reactants, that increases the number of collisions that occur per unit time. Now don't be fooled. In order to increase the concentration, you have to place more reactant particles in the same volume. It doesn't mean you just pour more of a reactant into your container. If you increase the concentration, it increases the number of collisions that happen. And this increases the probability that a successful collision will happen. The second thing you can do is play with the surface area of your reactants. Adding solid reactants as powder, so grinding them up, increasing the surface area, increases the number of reactant particles that are available to collide. This increases the number of collisions per unit of time and increases the probability that they'll hit at the right orientation and at the right speed. Adding solid reactants as chunks, which have a low surface area, slows down the reaction. Molecules in the center of the chunk are not available until the outside of the chunk has reacted away. Here's a diagram that shows that really clearly. If I add them as in a large chunk, I only have 12 particles available to react, only the ones at the surface. If I still have 16 particles and add them as smaller chunks, grind it into powder, then all 16 particles are available, so I'll have more collisions and a greater chance that they'll collide correctly, so therefore a faster reaction. The third thing that you can manipulate is the temperature you add your reactants at. Heating the reactants increases their kinetic energy, the speed the particles are moving. Now, this affects how fast your reaction goes in two different ways. Faster molecules collide more often. This increases the probability that they're going to collide successfully. Heating up your reactants also gives you more molecules with the correct amount of activation energy. Below is a diagram known as a Maxwell-Boltzmann plot, showing you how the kinetic energy of a sample of particles and its temperature are related. The temperature of a substance only tells you the average kinetic energy of your particles. That means some particles are going to be moving faster and some will be moving slower. This is shown by a classic bell curve. The blue line here, T1, shows you the different amounts of energy particles in a single sample have. The temperature of the sample would be around here, about the average. You will have particles that are moving faster to the right of the center of the peak, and you will always have particles moving slower to the left of the peak. Now, if this is the activation energy, only a small fraction, represented by the area underneath the curve, will have the sufficient enough activation energy in order to do the reaction. Now, if you heat up the sample, you squish this curve out. You will always have particles that have very, very low energies, no matter how much you heat up the substance. By heating it up, you will change the temperature. You slide the average further to the right, the top of the curve. And that gives you more particles, a greater fraction of your sample, having the required activation energy to do the reaction. The fourth way you can manipulate a reaction speed is by adding a catalyst. A catalyst is a substance that speeds up a reaction, but it is not consumed by the reaction. They work by providing a different reaction mechanism, so different steps to achieve the same overall reaction, and each step has a lower activation energy. This often involves grabbing reactants separately, then lining them up so that they collide at the proper orientation. An example of a catalyst would be an enzyme. Here's a potential energy diagram showing a reaction that's uncatalyzed. We have an exothermic process because our reactants have higher energy than our products do. Here's the uncatalyzed line. We got a transition state way up here, and then we go down the hill to our products. If we add a catalyst, instead of doing the reaction in one step, it can do it in 2 or 3 or 4. Now each step would have its own activation energy, and those activation energies would be lower than the uncatalyzed reaction, which means more of your particles could perform the reaction if the proper collision is made.